Hi kids, it is Sunday evening at 10 after 6 and let's get the velocity vector party started. Okay, so when you deal with vectors and how we treat them in physics, this is one of those deals that you already intuitively understand the process. I just have to convince you that you already know it and how to make sense of it. Okay, so trust me on this one. So initially we're not going to deal with any trig functions. This is going to be the graphical stuff. And the reason that I go through this whole process of showing you the graphical method is that 1 year I was short on time and I skipped this and I went straight to the trig functions, and it was just a train wreck because you didn't understand how things fit together. And so if I skip this step, I'm going to pay for it later on. So we're just going to go through and make sure everybody gets this first step out of the way. Because if you understand that, then the trig functions, part of it, become much easier to deal with. So here's the setting. So let's say that you're going to have a tug of war, okay? And you're going to have, out of first block, the Riley of your choice, okay? Because I've got two of them, okay? So the Riley of your choice is going to pull this way with a force of 10 newtons, okay? And out of third block, I'm going to have John pull with a force of 5 newtons this way. So here's the first thing that we have to get straight. Is that vectors are like force vectors especially, and it could be velocity, it could be acceleration, it could be displacement. I'm just going to use force, okay? It doesn't make any difference what the vector quantity is. But here's a certain set of rules. Rule number 1 is that all angles are measured from a positive x-axis, and that's defined as 0 degrees, okay? So here's 0 degrees. This, no matter what, if I say 0 degrees, this is what I mean as 0 degrees, okay? This isn't 0, this isn't 0, this isn't 0. Positive x-axis, that's 0 degrees. And then we're going to measure all the angles counterclockwise around from that point, okay? So like you're never going to have, like if you're over here in the 4th quadrant, this isn't going to be like negative 40 degrees. All angles are going to be measured around like this. So here you have 90, you have 180, you have 270. You can go all the way up to like 359.9, and then you're back to 0 degrees. So this is going to be important. So when I say, hey, when I'm talking about vectors, and I say I've got a 90-degree angle, I know I'm going to be right here. It isn't going to be over here. It isn't going to be down here. 90 degrees is going to be straight up. 180 degrees is going to be over here. Here's going to be 270, 350, whatever that is. So no negative angles, okay? That's rule number 1. So if I want to describe this vector, because if I just say force Riley is at 10 newtons, I don't know what that means. Is it 10 newtons up, 10 down, 0 degrees, 90 degrees? I don't know. Because the 10 newtons, remember, is just the magnitude. So I have to give it a direction to make it a true vector quantity. So if I go 10 newtons at 0 degrees, oh, okay. Now, as soon as I put the at 0 degrees on it, now it becomes a vector quantity. If I just said 10 newtons, that was just a scalar quantity because I didn't know which direction it was pointing. But if I say 10 newtons at 0 degrees, now it becomes a vector quantity. Now, I'm going to do the same thing over here. So here's force John, right? That's going to be 5 newtons at 180 degrees. Now, this isn't negative 5, okay? It's 5 newtons here. It's 10 newtons here. Now, notice on this one, the magnitude is represented by the length. So this is 10 newtons, right? So that's quite a bit bigger this way. And I got 5 newtons that way, which is about half that length. Oh, okay. So the length is going to be representative of the magnitude of the vector. So I got 10 at 0, I got 5 at 180 degrees. Now, if this was the tug of war, this is what you all would go, oh yeah, Riley is going to win by 5 newtons, and it's going to go in this direction. Okay, that's it. So what you all just did without knowing is that you just did the vector addition of, or excuse me, the graphical addition of vectors using the tip-to-tail method. And you're going, oh no, we didn't, Burkamp, that just makes sense. Well, that's what vectors do. They just make sense. So when you're going to add these vectors tip to tail, there's a couple of steps, and these are laid out on the back side of the assignment. So if you go back over here, it says steps in the graphical addition of vectors using the tip to tail method. Okay, so they're over here. Okay, don't make this difficult. So here's what you're going to do. When you sketch these like this, and we're going to do this a lot, when you sketch it like this, when you have like, here's the ring, Riley's pulling this way, John's pulling this way. So if that's the case, then this is what we call a free body diagram. Okay? Usually just call it FBD. So on a free body diagram, and this is particularly true with forces, is that you pick a center. It could be a block of wood, it could be a spaceship, it could be the moon and the earth. It doesn't make any difference. You pick a center and you say, okay, here it is. And then you draw all the forces acting out from the center of this. So on a free body diagram, this is what this is going to show. I don't know what the net effect is. This is just showing these forces acting from a common center. So when we get into vectors, especially with forces, okay, you're going to see this a lot where you're going to be asked to draw a free body diagram. So you pick a center, you say, okay, here's this vector, here's this vector. If there were other vectors, you would draw them coming out from the center like this. Okay? Pretty simple. Now, so with that said, so to actually go through and try and find the resultant. Now, let me talk about the resultant. This is the whole key to any vectors. The resultant shows you like the net effect of what these vectors are doing. It might be forces, it might be accelerations, it might be velocities, it might be displacements, okay? But the resultant just shows you, hey, when we get all done, what's the net effect of all these vector quantities acting? So this is what we're always after, is the resultant, okay? So let me show you how this is going to play out. So you're going to come in here and you're going to draw a line to some scale. And we're going to label this force Riley, which is 10 newtons at 0 degrees. Okay, so we drew this first vector. Boom, here we go. This now becomes a whole new coordinate system at the end of this. Okay, so the only thing you use force Riley to do is to tell you where the end of this vector is. Now, from the end of this, now we're going to draw the next vector. Okay, so the next vector was force John, right? So that's going to be coming back this way. So from the end of this one, we're going to draw a line back like this. And there's force John, which is 5 newtons at 180 degrees. So the whole point of these vectors is to graphically show what is happening. So I got Riley pulling this way. I got John pulling back this way. Okay, those are the only two vectors that we have. Now we need to draw the resultant. So on the back side over here, okay, on step number 5, I've got the letters RU. Okay, it's kind of an Australian thing. This is going to be a horrible kangaroo that I'm going to draw, so my apologies to all my Australian mates. Okay, so there's a kangaroo. Okay, good on you. There's a RU. Good on you. So the RU stands for the resultant goes from the origin out. Okay, so this is what RU stands for. Resultant is from the origin out. So when I draw this resultant, I'm going to go from where I started to draw the very first vector. So I go back to the origin. So this is what this O stands for. Here's my origin, okay? Then I'm going to go out from there to wherever I ended up. So in this case, I'm going to draw that vector out from that origin out like this, okay? And then I'm going to measure this, okay? So you guys are actually going to take like a meter stick or ruler, and you're going to measure this length. So in this one, that would be 5 newtons. So this is going to be my resultant. So we signify a resultant with a capital R, and then we put an arrow over the top of it that says, this is the net effect, this is the resultant, this is the vector, this is what we're after, okay? So this is going to be 5 newtons. Now, at this point I would ask the class, and I would say, hey, are we done now? And hopefully you all would say, oh, Mr. Burkamp, don't be silly, okay? Jennifer Prue is sitting over there going, seriously, Mr. Burkamp? We all know that you're trying to trick us, because that 5 newtons is just a magnitude, and there isn't an angle with it. So here's what's important. This is why you have to go from the origin out to this point. So I've got to put that at 0 degrees. So this is why you draw this vector from the origin out. Because if you drew it back this way, then you would say, Riley is pulling this way at 10 newtons, John's pushing that way at 5, but we're still going to go in the direction that John was pushing, even though he was only pushing with a force of 5 newtons, which doesn't make any sense at all. So this is why you always go from the origin out. Now, this is as simple as it gets, but if you understand this process, everything else is just going to follow suit, okay? So, here's my resultant, 5 newtons at 0 degrees. Now, some people like to think about this in terms of like steps, okay? So imagine that I'm here, and I take 5, or let's say I'm here, I'm going to take 10 steps this way, okay? And then I'm going to turn around, and I'm going to take 5 steps back this way. Now, at this point, Ellie Canizzo says, hey, Mr. Burkamp, you forgot your bag of chips. You need your bag of chips. So she's going to walk this way and bring me my bag of chips. So she's going to walk 5 steps this way to bring me that bag of chips. So I took 10 steps this way. I went back 5 steps. This shows the net effect of this. So this is what Ellie has to do to get me my bag of chips. Got that. Now, like I said, this is as simple as it gets. I'm going to get a little bit more complicated here. Okay? So, let's say that we're going to have a soccer ball. Okay? And we're going to have Colin kick the ball this way with a force of 10 newtons at 0 degrees. Okay? So we're going to have Colin kick the ball this way at 10 newtons at 0 degrees. Now, at the same time, I'm going to have Paige kick the ball this way with a force of 20 newtons at 90 degrees. Okay? Now, written like this, okay, written like this and drawn like this is a free body diagram. So this is 10 newtons, that's going to be 20 newtons. So this is force Paige. Okay? Now, if I said, hey, which direction is the ball going to go? You all would say, oh, it's going to go somewhere in between here like this. And then if I said, okay, hey, which direction is it going to go? Is it going to go closer to Colin, or is it going to go closer to Paige? And you all would say, oh, clearly, Mr. Burkamp, it's going to go closer to Paige because of the fact that she has more force. Brilliant. Again, you all intuitively understand this. If you look at this in terms of a tug of war, Colin's pulling this way, Paige is pulling this way, it's going to go somewhere up like this. So what I know is that the resultant is going to go somewhere up in this area. Again, draw them like this. This is a free body diagram. It shows all the forces acting from a common center. Okay? This won't give me the resultant, but it gives me an idea of what's going to happen. So I know that my resultant better be somewhere between 0 and 90 degrees, and probably a little bit closer to 90 degrees because this is the bigger force. Okay? Brilliant. Now, it gives me an idea of what's going to happen. So now we're going to repeat this process. So I'm going to come in here, and I'm going to draw force Colin, which is 10 newtons at 0 degrees. Now, imagine me cutting out this vector that represents Paige's, and I'm going to put hers right here. So imagine I could physically cut that out and drag it and draw it from the end of this. Remember, it's the tip to tail method. This just tells me where this vector ends. Then I'm going to draw the next vector from there. So from there, I'm going to go up like that. So here's force Paige, which is going to be 20 newtons at 90 degrees. So I've got one vector here, okay? So here's force Colin. Here's force Paige coming up like this. So then I'm going to draw that resultant. Now remember, the resultant goes, the root thing, good on you mate, goes from the origin out to here. Crikey! Crikey! So we're going to go this way. I should have brought my Australian hat to give this lecture. I'll do that next time. Okay, so I'm going to draw my resultant. And it's going to go like this. Okay? Now, eventually we're going to use trig functions, but not right now. So what you're going to do, this is why you have to have a ruler and protractor. So what you're going to do is you're going to take your handy dandy little protractor and you're going to measure that angle. Okay? So you're going to set here like this. In this case, I'd have like about 58 degrees. And then you are going to measure this length. So you're going to measure the length of this result. You're going to take your protractor, your ruler, and you're going to measure this length, and then you're going to take your protractor, and you're going to measure this angle. Now remember, you're always going to measure from that initial positive x-axis. In this case, one of my vectors just happens to be right here. So I'm going to go from this initial positive x-axis up like this. So I would say that resultant would be, and I'm just making this number up, okay? 25.6 newtons at 58 degrees. So what this tells me, okay, is that if Colin kicks the ball this way, Paige kicks the soccer ball this way, the net effect of that would be a force of 25.6 newtons at 58 degrees. Now, if you like the steps analogy, okay, I walked out here like this 10 steps. I turned and I walked 20 steps in this direction. Ellie wants to get me a bag of chips. So she has to walk from here to here at an angle of 50 degrees, and that's how far she has to walk to get me where I need to be. Okay? Cool with this. So here's the result. This is what you're after, is this result. Now, here's as complicated as it's going to get. Okay? So let's say that we'll go back with the soccer ball. Okay? And let me see. We got Caden is going to, we'll call this X and Y system. That's just going to confuse things. Let's not do that. So let's say Caden's going to kick the ball this way with the force of 20 newtons at 30 degrees. Okay? So now, we're not going to start on the x-axis. Okay? Here's force Caden, 20 newtons at 30 degrees. There you go. Now, let's say that we're going to have, hold on, let me pick that one. Let's see, who else do we want to have? Angelique, there we go. So we're going to have Angelique kick this way with a force of 30 newtons at 110 degrees. Okay? So here's the deal. So we got Caden kicking this way at 20. We got Angelique kicking this way 30 newtons at 110 degrees. We want to find the resultant. So again, drawn like this is the free body diagram. And this is just a sketch. But what this tells me is that that soccer ball is going to go somewhere up in here. So I know that my angle cannot be less than 30 degrees, and it can't be more than 110. It has to be somewhere in here, okay? And that's going to be 30 newtons, right? And that's going to be bigger. So I got to figure that that angle is probably going to be closer to 110 degrees than it is the 30 degrees. So here's what you're going to do, okay? You're going to take your protractor, and this is tough to do because you can't see this, but imagine that I'm laying this protractor down, and here's where I'm going to start, okay? Doesn't make any difference where I start, but this is where I'm going to start. So I'm going to sit here, I'm going to take this, I'm going to lay this down on here, okay? And I'm going to measure up 30 degrees, okay? So I've made a mark here. That line is going to be 30 degrees. So I'm going to measure that line. Like so. So that's going to be my 20 newtons at 30 degrees. Okay? So I'm here like this. Okay? I measured up 30 degrees. I drew that line to whatever length is going to represent 20 newtons. Now, here's the tough part. When I do that 30 newtons at 110, this now becomes a whole new X and Y system. So when I measure 110 degrees, I'm going to put that protractor like this, okay? And this is a whole new X and Y system, completely new. Don't measure 110 degrees like this. Don't do something wonky like this. Imagine that you are starting over from scratch. And you're saying, all I want you to do is draw a 30 Newton force vector at 110 degrees. So you're going to come in here and you're going to put your protractor like this, and you're going to measure up 110 degrees and you're going to put a mark, okay, right there. And then you're going to draw that vector. So that's what I'm going to do, okay? So trust me on this one. So even though you can't see it, this is what I'm doing. Okay, so there's my mark. And then I'm going to draw that. Hold on. That was supposed to form like a straight line. There we go. Okay. So this is force Angelique, which is 30 newtons at 110 degrees. Now, here's the most important step. It's going to be your resultant. My resultant is going to go back to this initial origin right here. I'm going to draw it out. I'm going to draw it up like this. Okay, so I'm going to go from this point up to this point. So you're going to take your protractor or your ruler, and you're going to lay that down, and you're going to draw that line. So I'm going to go from here up to that point. So, and then you're going to measure that length. That's the easy part. The angle though, now listen to me, listen to me, listen to me, listen to me. When you measure that angle has to be from this initial positive x-axis. I don't want this angle in here. This isn't the angle that I want. Okay, this is not the angle that I want. What I want is from that initial positive x-axis. And the reason that I want it from that initial positive x-axis is because that's how all angles are defined. Because if you measure this angle, and let's say it's 28 degrees. Well, if you tell me 28 degrees, I'm going to think I'm going to start from here and go up 28 degrees. This is why you always have to measure back to this initial positive x-axis. So I'm going to put this protractor like this. I'm here, and that's going to be like, say, 83 degrees. So I'm going to measure that length, okay, and let's say I'm just going to make up the number. I measure that length and I get 42 newtons at 83 degrees. So that's my resultant. So here's what's most important. Again, if you go with the steps analogy. I started here. I'm going to take 20 steps at 30 degrees. I'm going to stop. I'm going to go left. I'm going to go 30 newtons at 110 degrees. And I'm here. Ellie Canizzo has to give me a bag of chips. So she's going to take 42 steps at 83 degrees. So this is why I can't measure this angle. Because this angle in here, if it was like 28 degrees, so if Ellie still took off at 28 degrees, she would think she's going to go somewhere up like this. So if I tell her to go 42 steps at 83 degrees, she's going to come in here to that initial positive x-axis, and she's going to measure around like this, 83 degrees, and that's what she's going to take off to. Okay? So this is as complicated as it gets. Is when you have angles that aren't at 90 degrees. So on this sheet, let me get you started. The first thing you're going to do is you're going to have 5 vectors, A, B, C, D, and E. Up here at the top, I tell you like vector A is 5 centimeters at 0 degrees. So these are the 5 easiest points you will ever get in this class. All I want you to do is draw these vectors. That's it. Now, if you want to draw them all from the same common center, okay, and again, don't use grids, okay, don't use graph paper grids. Some people would like to draw this on graph paper, some people would like to draw it on plain paper. I don't care. But what you can't do is say, oh, I'm going to let 5 grids be 5 centimeters. You can't do that. You actually have to measure out with your ruler 5 centimeters. Now, when you do this, let me give you a word of advice, okay? What you want to do is measure out 5 centimeters, okay? So there's your 5 centimeter mark. Don't put the arrowhead on the end of that, or otherwise it's going to be longer than 5 centimeters. So measure that thing out at 5 centimeters and then put that arrowhead back like this so that it doesn't make it longer than 5 centimeters. So you're going to label this, oh, here's vector A. Now, vector B is going to be 3 centimeters at 90 degrees. So if you want to, this is a personal preference thing, if you want to come in here and go, oh, I'm going to draw vector B here, okay? And then you got vector C, and if you just want to draw them all from the same center like a starburst, you can. If you want to draw them all separately and go, oh, here's vector A, here's vector B, vector C is 4 centimeters at 120 degrees, whatever that is, okay? If you want to draw them separately, I don't care. If you want to draw them all from the same center, it's whatever works for you. Okay. Now, once you get that done, and make sure that you label these vectors, okay? Especially because you're going to be taking pictures of these. Label them, keep everything completely separate, keep everything very organized, please, I beg of you. Okay, so now, on number 2 down below, you can take vector A and you're going to add that to vector A. So here's what you're going to do. You're going to measure out 5 centimeters. Okay, here's going to be vector A. From the end of vector A, I'm going to add vector A again. Okay? Now, in this situation, this is as simple as it gets. It's vector A added to vector A. So then, my resultant then is going to be from the origin out to that end. Okay? So my resultant is going to be 10 centimeters at 0 degrees. So here's going to be number 2. Okay? So, on another sheet of paper, not here, on another sheet of paper, you are going to draw this, and you make sure that you clearly identify, oh, here's number 2. Okay? Because I have to be able to see what these are. Don't make me guess and try and muddle through these. I'm not going to. It's going to be a train wreck. Don't. Okay? Label them. Here's number 2. So what you're going to write on your paper, right there besides number 2, where it says A plus A, what I want is the value of the resultant. So there where it says A plus A, and you've got this line, you're going to write 10 centimeters at 0 degrees. So what that tells me is that this is the net effect of these two vectors of A plus A. Now, in this situation, it is just 5 plus 5. Don't think that's always going to happen, because if you have like different angles, you just don't add together the magnitudes and go, oh, there it is. So, let me make a sketch on what some of these are going to look like. So on number 3, you're going to add vector A to vector B. So you're going to draw vector A, okay? From the end of vector A, you're going to draw vector B. So vector B is 3 centimeters at 90 degrees. So from the end of this, you'd come up like this. And again, these are just sketches. Then you're going to measure that, you're going to draw that resultant. Okay? So again, here's what you're going to do. You're going to put in here that protractor like this, and you're going to measure this angle. And then you're going to measure this length. So this might be like 6 centimeters at 35 degrees, whatever this is. Now, use your measuring devices. Your angle here, your protractor, is marked off to like the whole degree, so you can easily estimate the 1/10 of a degree. So if that's like exactly 35 degrees, oh, put it as 35.0 degrees. If it's halfway in between, oh, that might be 35.5 degrees. Okay? Use the precision of your measuring device. And then you're going to take your ruler and you're going to measure that length from here out to here. Because again, I walked here, L is going to take this path to get to this point. Okay. Now, where it gets a little bit more complicated is when you get down to number 4. So on number 4, this is just a sketch. I'm going to draw vector B, which is 3 centimeters at 90 degrees. Now I'm going to do vector D. Now vector D is, when you see this, it's 6 centimeters at 250 degrees. So this gets a little bit dodgy. So, to get to 250 degrees, again, I'm starting here as an X and Y coordinate system. I'm going to measure around here to 180, and then I'm going to measure another 70 degrees past that. Because if you take 250 degrees minus 180, you get 70. So what I want to do is I'm going to put my protractor like this. So there's 180, and then I'm going to measure 70 degrees down like this. And I'm going to put that mark right there, okay, which is about like here. So then I'm going to draw, here's vector D. So the resultant then on this one, I'm going to go from that origin out to that point. Okay? Now, here's what's important. When I measure this angle, it has to be from here all the way around to here. So again, this is just a very, very, very crude sketch. But it tells me that that angle has to be more than 180, but less than 270. So it's going to be somewhere here in this first, second, third quadrant. Somewhere between 180 and 270. So you're going to take your protractor, put it up here like this. You're going to measure around, like I had like 31 degrees. So I would take 180 and add that to 31 degrees, and I would say, oh, that's so many centimeters at 211 degrees or whatever that is. This is not the angle. I'm just showing you how to do this. Don't think that the answer to number 3 is 210 degrees. This is just such a crude sketch. But here's the point. Again, you walked out here, this is the net effect of this vector. So when you're doing this, take your time. Do not crowd these together. Leave lots of space. Clearly label them. Oh, here's number 4. Here's number 3. Do not intertwine these. Keep these completely, I say again, completely separate. You need a good sharp pencil. Do not do this with a dull pencil. You need a good sharp pencil. You need to take your time measuring the length of these lines. Be very precise in this measurement. Now, I know there's going to be a little bit of variance, okay? I know there is. But I'll give you like a couple of degrees on either side of what it should be, but that's about it. So, take your time, get an idea of how this deal is going to play out. So, if you're watching this on Monday, you're going to do the CART lab on Tuesday. If you're watching this on Tuesday, you've already done the CART lab, and there's that. So, that's kind of the story, kids. So, graphical addition of vectors, when in doubt, follow the steps. The only thing I want written on this sheet, on these lines, is the value of the resultant. But again, I should be able to clearly look at another sheet of paper and see what those are. So when you send in the CAM scanner, I want this as page 1. Then I want everything else on separate pages. Please, when you're taking pictures of these, keep them in sequence, okay? You might even like if here's like a page, maybe label that like page 2 and then maybe page 3, because that way when you're taking pictures of it, you know which sequence to put it in so that I don't have to guess the sequence. So, anyway, good luck, kids. And we're all counting on you. All right, see ya.